distinguished guests, please have a seat.
Excellencies, our distinguished guests. Without further ado, we would like to invite Dr. Ing Wahyudi Hasbi as the chair of the IEEE Indonesian section to deliver welcoming speech. Please give a warm applause.
Distinguished guests, colleagues, researcher, professional, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Very good morning. Shalom, Om Swastiastu, Namo Buddhaya, Salam Kebajikan, a prosperous and warm greetings. First of all, please allow me to greet the Excellencies Vice Rector 3 Jember University, Professor Dr. Bambang Kuswandi, representing the Rector of Jember University, my colleague, Professor Insinyur Ain Afandi, STMT, IPM, Senior Member of IEEE, PhD, Dean of Faculty of Engineering, my colleague as well, Dr. Triwahyu Hardianto, STMT, Chairman of the iceicit Committee, Professor Bambang Sujanarko, keynote speaker for today, Dean Sarafi from IEEE Power and Energy Society Asia Pacific, and also keynote Professor Dr. Insinyur Bayu Jayawardana from University of Groningen, Dean of the Faculty in Jember University, along with other invited guests, all distinguished keynote speakers, committee, all participants, ladies and gentlemen. It's such an honor and pleasure for me to be able to greet you all and give a few words to represent the IEEE Indonesia section at the opening of this conference, and also apologize for not being in person for this conference. On behalf of the IEEE Indonesia section, I would like to express my sincere gratitude and welcome you to the International Conference on Electrical Engineering, Computer and Information Technology, or iceecit 2022. And this conference is hosted by Universitas of Jember and also supported by IEEE Indonesia. And the goal of this conference is to facilitate researchers, practitioners, and lecturers around the world to publish, explore, and share their current research in electrical and electronics, computer and information technology. Distinguished guests, colleagues, researchers, professional, ladies and gentlemen, engineering, especially electrical engineering, has helped solve our daily problems and our production needs by applying scientific knowledge, technical methods, design, and management principles. Indeed, engineering, with its range of subdisciplines, has been a prime contributor to the survival of humankind on Earth and to improving our quality of life. We are also aware that the digital technologies are capable to induce digital disruption and thus have far-reaching effect on the business environment of incumbent organization. In order to remain prosperous, it's crucial to foresee the trajectories of technological changes, to assess related threats and opportunities, and to strategize accordingly. And for that reason, appropriate method must be utilized to build the knowledge foundation for deriving effective digital transformation strategies. In such so, I believe that the theme of this conference is very important in highlighting the innovation to accelerate the shift to innovation and transformation for digital era in the global community. Distinguished guest, keynote speaker, ladies and gentlemen, IEEE Indonesia as a regular organizational unit of IEEE was founded in 1988, and over the past 34 years, IEEE Indonesia has contributed significantly to have various activities that encourage science and technology for humanity in Indonesia. Together with volunteers, members, and all stakeholders, IEEE Indonesia has produced various activities by supporting more than 70 high-quality conferences every year, including supporting this conference. Compared with the previous year, in 2021 itself, the conference supported by IEEE Indonesia is increased by 50%. And as we all know, the high qualified conference paper within the scope of IEEE are published in the IEEE Explore Digital Library, indexed by Scopus, Web of Science, and any other major databases, with more than 6 million publications and more than 15 million downloads every month. As we also aware, IEEE also developed industrial standards such as IEEE 802 as a standard Wi-Fi that we use in our daily life. In electricity standard, the standard 1547 has been foundational document for the interconnection of distributed energy resources with the electric power system or the grid. Now we have seen a lot of the technological in electric vehicle, and a lot of standard has been already developed also in IEEE. In Indonesia, we also hold more than 40 professional, technical, non-technical, and administrative activities every year for all our members. And currently, we have more than 2,400 Indonesian members and more than 80 senior members, consisting of professional, industry, academia, and government researcher. We also supported 26 technical society chapters and joint chapters, 34 university students, and 9 IEEE student branches chapters, including I think in Universitas of Jember as well. In 2021, we already established a cooperation agreement with Directorate General of Higher Education, Research and Technology, in which we are actively supported and synchronized the Indonesian Ministry of Education, Culture, Research and Technology program, including taking part in the Campus Merdeka, Merdeka Belajar, or Independent Campus Freedom to Learn. Of course, this historical collaboration will strengthen the development of Indonesian higher education, especially the 8 leading indicator of higher education in Indonesia. We are also exploring the cooperation with Indonesian industries in various activities and is actively involved in providing inputs in preparing related government regulation. We are also signed an MOU already a few months ago with Indonesian Telecommunication and Digital Research Institute, which is also known as a Telkom Corporate University, in learning, research, and innovation collaboration through publication, empowerment, and education to develop Indonesia's technology leadership, innovation capability, and digital talents. Ladies and gentlemen, in this occasion, I would like to express my gratitude to all of the committee who have worked very hard in preparing this high qualified IEEE conference, and of course to Professor Bambang and all the colleagues. Is a very good work that your team has been done, and I'm very aware that putting together a conference of this size is not an easy task. Therefore, I sincerely hope for your active participation and cooperation in all of this conference program. I hope all of you will have an enjoyable and valuable experience during this conference events. Please share your best knowledge in your area of research and professional activities. Please stay active, stay healthy. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you for Mr. Wahyudi for the welcoming speech.
Next, we will listen to a welcome speech from Professor Insinyur Arif Nur Afandi to deliver a welcoming speech as a chair of the Power and Energy Society Chapter PE 31.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Honorable speaker, colleagues, professors, lecturers, researchers, ladies and gentlemen. On behalf of the Power and Energy Society Chapter, I would like to express my deep gratitude and recognition to the executive 2022 for the step. And this is a new event of the international conference which is held by Electrical Engineering Universitas Jember will become a flagship moment in this year. I believe that this conference will use to review current issues, current intention in engineering and technology with its limited aspect and huge implementation and application. As we know, the engineering and technology is very important to increase our humanity, our information, our shared knowledge around the world. So the ICT 2022 is one of the most important things to share our information around the world. As the other content service, the chapter of the article open for collaboration to achieve its objective of providing an effective way for automatic solution, researchers and practitioners to I also I also hope that this forum will make us become youth of the family in engineering and technology for development and other important activities. I also hope all participants stay on a very productive content with exciting and encouraging discussion that's together with the future of knowledge, research and technology for humanity and sustainable. Moreover, I wish this forum will give us full discussion of the future and SDGs issue on the right track to collaborate more with all academicians, researchers, practitioners along the world based on their expertise as utilization generation, especially to place the industrial revolution platform of that the internet and technology in control of energy and other related in electrical and other information system also important thing to address current issues and knowledge. Both the executive 2022 and also believe that this event will help the exchange of the ideas between all participants. Literally, the chapter 20 and 22 and ensure that our synergy will make abundance in engineering and technology for advancing basics, knowledge, and technology. Finally, my deep gratitude goes to all participants who joined PES chapter and you wherever you are. This is the fruit of our collaboration later, not only in content but also other activities and scientific and technology research and development as we are together in the power and research. The previous chapter also supports all of the engineering activities based on the relative define relative topic and related issue around the world. So it is important I invite you to join the previous chapter, including in English. I hope the next year the institute will meet up again for us. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Thank you, Mr. Afandi, for the welcoming speech.
For the next, let us welcome the Vice Rector of the University of Jember, Professor Dr. Andes Bambang Kuswandi for his welcoming speech, and request that Vice Rector of the University of Jember officially open iceecit 2022 by hitting the gong as a symbol of the opening of the event.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Honorable Chair of IEE Indonesia, Honorable Chair of Power Energy Section Chapter, and also Honorable Dean of Faculty of Engineering, Dr. Triwahyu, Honorable Professor from Faculty of Engineering, and also Honorable Head of Electrical Engineering Department, University of Jember, dear distinguished speaker, dear committee, and dear colleague and participant of this conference. First of all, I'd like very good morning to all of you in this hybrid conference of the first international conference on electrical engineering, computer and information technology, or call it iceecit, maybe I say easy compared to iceecit. So I just say iceecit can be held today. First and foremost, I would like to express my deepest gratitude to Allah Subhanahu wa Ta'ala, the Almighty, to giving us the time and chance for conducting this international conference, iceecit 2022. It is great privilege and pleasure for me to welcome all of the iceecit participants. I wish to congratulate the Faculty of Engineering, especially the Department of Electrical Engineering, that already organizing this conference and support for their effort and the spending their time in putting this event together, promoting the electrical engineering, computer and information technology and their allies. In cultivating an exciting interdisciplinary approach in this field as one of the state university in Indonesia, University of Jember try to implement an active approach in finding ways to improve imaginative work that contribute toward the advancement of the country throughout significant expansion of time, despite COVID-19 pandemic that still around us, and also in world where country, including Indonesia, that felt the effect of this pandemic. After the pandemic slowdown in some country, including Indonesia, we are exceptionally pleased to see the Faculty of Engineering, especially the Department of Electrical Engineering, has grown tremendously and have commitment to continuing our mission to promote University of Jember at international level, particularly even throughout this conference event. We are confident that this conference will be a hybrid meeting platform for electrical engineering, computer and information technology researchers that share and exchange breakout idea with one another, who thusly provide thinking, making successful joint effort and collaboration later on after this conference. The electrical engineering, computer and information technology are in line with our strategic plan of the University of Jember in us to develop University of Jember as a center of excellence in research and innovation internationally, particularly in industrial agriculture, biotechnology, and health sciences through advancement of digital technology, including engineering, electrical engineering, computer, and ICT. We believe that iceecit 2022 with the international participant and speaker will contribute to making UNED on par with any reputable university around the world. To all the keynotes, plenaries, and invited speaker and all participants, we sincerely hope that this conference will serve as a platform to create and strengthen collaboration in international level and locally. And finally, it is my fervent hope that this conference will produce many scientific discussion, sharing idea and collaboration later on. And I wish all participants to this conference a wonderful conference at iceecit 2022. On behalf of the Rector, University of Jember, because today we have three type of event. Big event first is this event, iceecit, and the second we also have the colloquium, University of Jember, and the second is we have a seminar on the creative digital technology, which is also held at the same time and also the same day. So our rector appoint me to present his speak in this conference. On behalf of rector, again, by reciting Bismillahirrahmanirrahim, I officially open the iceecit 2020. Thank you for all the participants and hope you will enjoy this conference, and later on we could make a wonderful collaboration either through the local participant or via national or even international collaboration. Thank you. Assalamualaikum warahmatullahi wabarakatuh. reciting Bismillahirrahmanirrahim. Again, I officially open this iceecit conference 2022 with Bismillahirrahmanirrahim.
Recording in progress.
Before we go to the next agenda, we invite Mr. Bambang Kuswandi, Mr. Triwahyu Herdianto, and Mr. Bambang Srikaloko to sit in the seat audience provided.
Honorable distinguished guests and distinguished speakers, as our welcome greetings, we would like to present to you a traditional welcome dance choreography to symbolize our dedication to welcoming the arrival of guests as a way to show hospitality and respect. It is performed in a special dance called Tari Labako. Please welcome Labako Dance by Jember Art SMA. Thank you for the stunning performance of the Lapago dance, which welcomed the audience here.
Next, we will pray, so God will also bless all that is obtained here. The prayer will be led by Mr. Mahros Darsin, PhD. Please, Mr. Mahros Darsin, PhD, go to the podium stage.
Assalamualaikum warahmatullahi wabarakatuh. We will lead prayer in Islamic ways. So the other beliefs, let's pray according your own belief. Bismillahirrahmanirrahim. Alhamdulillahi rabbil alamin. Allahumma la uhsi sana'an 'alaika anta kama asnata 'alaya nafsik. Oh Allah, I am unable to praise you as I should. You are as you have praised yourself. Allahumma salli ala Muhammadin wa ala ali Muhammadin kama sallaita ala Ibrahim wa ala ali Ibrahim innaka Hamidum Majid. Allahumma barik ala Muhammadin wa ala ali Muhammadin kama barakta ala Ibrahim wa ala ali Ibrahim innaka Hamidum Majid. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. O Allah, grant us the good of this world and the hereafter, and save us from the fire of hell. Rabbana amanna faghfir lana warhamna wa anta khairur rahimin. Our sustainer, we believe in you, so forgive us and have mercy on us, and you are the most merciful. Rabbana atmim lana nurana faghfir lana innaka ala kulli syai'in qadir. O Allah, our sustainer, complete for us our nur and forgive us. Verily, you have power over everything. Allahumma ahsin akibatana fi umuri kulliha wajirna min khizyi dunya wal akhirah. O Allah, make the outcome of all our tasks good and save us from the humiliation in this world and the hereafter. Allahumma inna nas'aluka al-afwa wal afiyah fid dini wad dunya wal akhirah. Oh Allah, we beg of you forgiveness and prosperity in this world and in the hereafter. Allahumma inna nas'aluka ilman nafi'ah wa amalan salihan mutaqabbala wa rizqan thayyiba. Oh Allah, we beg of you beneficial knowledge, good, accepted in your court action, and pure sustenance and cure from every sickness. Allahumma inna nas'aluka min khairi ma sa'alaka minhu nabiyyuka Muhammadin sallallahu alaihi wasallam wa na'udzubika minhu nabiyyuka Muhammadin sallallahu alaihi wasallam. Jazaallahu anna Muhammadan ma huwa ahluh. Subhana rabbika rabbil izzati amma yasifun. Wassalamun ala mursalin. Alhamdulillahi rabbil alamin. Amin. Assalamualaikum warahmatullahi wabarakatuh.
Thank you for the prayer guidance from Mr. Mahros Darsin. It is now my deep pleasure to introduce our moderator this morning, Mr. Abdurrahman. He received a PhD in Agricultural and Environmental Engineering United Graduate School of Agriculture Sciences, Tokyo University of Agriculture and Technology. And he is a lecturer at the Department of Environmental Engineering, University of Jember. Mr. Abdurrahman, please get on the stage.
Next, I will ask the moderator to lead the keynote speech section. The time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, Excellencies, IEEE, the Chair of IEEE Indonesia Chapter, Indonesia Section, Dr. Engineer Wahyudi Hasbi, Excellency, the Chair of IEEE Power Energy Society Indonesia Chapter, Professor Dr. Insinyur Arif Nur Afandi, Excellency, our Vice Rector of Universitas Jember, Professor Dr. Bambang Kuswandi, our Dean of Faculty of Engineering, Dr. Insinyur Triwahyu Hardianto, our Vice Dean of Faculty of Engineering, Dr. Dewi Yunita, and our Head of Electrical Engineering Department, Dr. Wijanarko. And I would like to express my special thanks to our distinguished speakers today, Professor Bayu Jayawardana from University of Groningen, Mr. Din Sharafi from IEEE Power Energy Society, and Professor Bambang Sujanarko from Universitas Jember. Welcome to International Conference on Electrical Engineering, Computer and Information Technology. We are now in the plenary session where we will discuss issues on electric power system, especially that relate to the climate change. Ladies and gentlemen, a lot of scientific reports in the last decade show clearly that the threat of climate change has been more and more imminent. And the climate change has been an essential issue for tropical countries like Indonesia. Indonesia is a large country with a population of more than 270 million. And all of these people are in need of affordable, sustainable food, water, and electricity. We all know that Indonesia is rich of renewable resources. We have abundant solar, hydro, geothermal, wind energies. However, the latest statistics issued by the Ministry of Energy and Mineral Resource show that the total installed capacity of our electric power system in 2020 was 72.75 thousand megawatt, and 85% of that level were based on fossil energies. And these fossil energies are major contributors to greenhouse gas emission. On the other hand, Indonesia has joined other countries ratifying Paris Agreement, in which Indonesia committed to the world to reduce greenhouse gas emissions by at least 32% from its business as usual emission level in 2030. So here we have a clear challenge: how to provide and maintain affordable, sustainable electric power systems while at the same time meet the target energy. And in addition, Indonesia is looking forward to become zero net emission country in 2060. So this is a tough question. And in this plenary session, we are trying to answer this question by first listening to the views of our expert speakers. We have 3 experts here with distinct expertise from electric power field. Let me introduce our first speaker, Professor Bayu Jayawardana. Professor Bayu Jayawardana is currently a professor of mechatronics and control of nonlinear systems in the Faculty of Science and Engineering, University of Groningen, the Netherlands. He graduated cum laude with bachelor degree in electrical and electronics engineering from Institut Teknologi Bandung in 2000. And then he continued his study and earned Master of Engineering degree in electrical and electronic engineering with full scholarship from Nanyang Technological University, Singapore in 2003. And then he completed his PhD degree in electrical and electronics engineering, again with full scholarship from Imperial College London, United Kingdom in 2006. Professor Bayu Jayawardana was with Bath University, United Kingdom, and with University of Manchester, United Kingdom. His research interests include the analysis of nonlinear systems, systems with hysteresis, mechatronics, robotics, and systems biology. He is a subject editor of the International Journal of Robust and Nonlinear Control and an associate editor of the European Journal of Control and a member of the conference editorial board of the IEEE Control System Society. I would like to say that Professor Jayawardana's profile is very shiny. He is an exemplary academician. He has received numerous awards and achievements, including senior membership of IEEE and Faculty Teacher of the Year Award for the Faculty of Science and Engineering, University of Groningen in 2017. And he's also a co-founder of Ocean Grazer BV, a startup company in ocean renewable energy systems in 2018. And he's also recently received a young professorship from Institut Teknologi Bandung. I would like to invite Professor Bayu Jayawardana to deliver his speech. Professor Bayu
morning.
Jayawardana, time is yours.
Yes, thank you very much. Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi. So it's my pleasure to be here, and in fact, it is actually my wish that I could join you all on site in Indonesia in Jember, but unfortunately, there are many obligations that I have to do here in Netherlands, which prevent me from going to Indonesia. But nevertheless, it's still again a privilege for me to be able to speak in this conference to tell a bit more about our recent effort to allow the energy transitions toward the renewable energy through the technology that we have developed. So let me try to share my screen. And I hope that I'm able to share my screen. Yeah. Now, so what has been mentioned earlier by moderator that we are now facing with the threat of the climate change, and we need to transition ourselves to clean energy in order to be able to deal with the carbon emissions and try to minimize the damage that has been done in the earth. So towards this goal, we have developed a number of different technologies for the past couple of years together with my colleagues and team, in particular within the Ocean Grazer team, where we are looking into ways to harvest energy from the oceans. And at the same time, we try to look ways not only to produce the energy, but also try to produce it in a reliable and a constant way. So in that case, then we need to have a storage device which are able to store the energy on site that enables us to have a continuous productions of energy, where if there are some time period where the energy is abundant from the sun or from the wave, we can harvest those energy and store it in a certain storage device on site, so that later when the amount of energy is no longer available, it can always happen in offshore that night is coming, so then the sun can no longer be harvested, or the wave is suddenly having a low energy, then we are no longer able to harvest the wave energy. We can tap the energy that has been stored in the storage device to again produce the electrical energy to the grid. So that is basically our intentions, to try to be able to produce a constant energy at any given time. So that is the main topic of my presentation today, which is about the hybrid offshore energy solutions. At the moment, I'm also the scientific advisor of the startup company that has been set up in recent years, Ocean Grazer BV, but I'm also the professor of mechatronics and control of nonlinear systems at the University of Groningen, as has been mentioned earlier. So let me present a short movies about our technology.
People around the world are passionately contributing to a successful transformation to a sustainable society. Towards this transformation, we need to switch completely to renewable energy. It needs to be available 24/7, all year round. Imagine we could produce renewable energy when the wind is not blowing, or during the night when there is no sun for solar energy. What if we could balance supply and demand at any given time? There is a huge potential renewable energy that remains unused. Ocean energy. The Ocean Grazer provides a hybrid solution to tap into that potential by combining offshore wind and wave energy production with storage. Its unique storage solution provides flexibility that is crucial to balance the supply and demand. It ensures that energy is available when you need it. Waves contain a lot of energy. However, each wave is unique. That's why the Ocean Grazer's innovative wave energy converter adapts to the incoming wave heights and periods. By using multiple floaters in a floater blanket, we can cover a wide spectrum of waves simultaneously. Sensors measure the wave characteristics and communicates them real-time with the intelligent control system. This system computes the optimal configuration of our floater blanket, enabling us to harvest the full potential of each wave. The smart combination of wind and wave energy production in a single platform results in a high yield of energy. When the energy production exceeds the demand, the Ocean Grazer utilizes its environmentally friendly storage system. It stores energy by pumping a fluid into flexible bladders. By using the pressure of the ocean to deflate the bladders, electricity is produced when it is needed, resulting in a stable supply of renewable energy. Our hybrid energy solution increases resource efficiency by combining different renewable energy sources in one location. The collective use of infrastructure increases the efficiency even further. The Ocean Grazer is scalable and modular. It can be used in different configurations. Currently, we combine wind, wave, and energy storage, but in the future, any combination is possible. Together, we transform our society into a sustainable future.
So these movies shows you a number of different technology that we developed within the Ocean Grazer, within our startup company, but also at the university. And at the moment, we are focusing on the storage solutions, while the extractions of the wave energy is still going on in our research group, as well as my colleague at the university. So let us tell you briefly, why do we need such kind of solutions? First of all, we know that European Union is currently investing a lot in increasing the renewable energy capacity, including the offshore wind capacity, where we have projected, or where we have installed 20 gigawatt capacity of wind already in Europe. And the ambitions is that the European Union would like to increase this further towards 80 gigawatt by 2030, and even to reach the climate goal, we need to extend it even further to 450 gigawatt by 2050. Now, of course, with the introductions of many offshore wind turbines, or also with the offshore solar park, that introduces some important challenges, in particular that there will be mismatch between what is available and what is demanded by the market. And we know that wind is always weather dependent. So sometimes the energy from the wind is very high, but at other time, the supply from the wind can be very low for some cases, depending on the weather. While we know as well that the demand of the electricity from the industry or from the consumers vary as well throughout the day. And there must be a balance between the supply and demand. And if there is no a proper balancing methodology of the supply and demand, then we know, of course, that there will be instability in the grid. So in particular, the power systems becomes unstable. And this picture shows you pictorially that we may have an oversupply of energy when the demand is low, and we need to somewhat capture this potential, and we should be able to use it when the demand is high, while the renewable energy sources potential is low at some time period in the future. These things has happened as well in the past. So I'm trying to show you here real data from April 2020, already a couple of years ago, where the availability of renewable energy that can at some day very high while the demand is very, very low. And this happens in Germany, where the price becomes negative. So in this case, actually, the customer and the industry, they will receive money if they can consume the energy at those time period. And of course, this is not a good business case for many utility companies, because in this case, then they are actually paying their customers just to absorb the extra energy that they produce. So nobody wants to sell at the negative prices. And when we are looking at the ambitions of having hundreds gigawatt energy capacity in offshore, we should try to prevent such cases to happen. So when the energy is produced very large offshore, there should be a way or mechanisms to store those energy. Now, large-scale offshore energy storage is needed in this case, and we need to solve the problem at the source. And the offshore energy is needed because we wanted to prevent, as I have mentioned earlier, negative prices. We want to prevent the need to expand the grid and prevent the cost and impact of storage that has been installed onshore. So why do we need this? Because we would like to store the energy on the site so that we are not actually utilizing the capacity on the power transmissions only just for the sake of storing the energy. Now, if you take a look into the current energy technology, there are various different technology available in the market. We have, for the short term, we can use batteries or electrochemical batteries to store the energy within seconds or minutes. We already know it from many different solutions in that aspect. But if you would like to store the energy for a longer period of time, there are many other technologies such as hydrogen technology, for instance, or storing it as other chemicals, compounds. But if we are looking at hours or days, we could, if we are onshore, we could store it in the pumped hydro systems, or we can store it in the dam, like what we used to have in Indonesia. Now, if we are looking the solutions to the offshore, there is technology that is missing in this diagram because there is no analogy of pump hydro mechanisms that can be placed offshore. And that is the technology that we would like to develop within the ocean grazer. So how does it work? So basically we try to capture the essence of a pump hydro storage plant, but we are not installing it on land, but we try to find the solutions at the bottom of the sea. So the diagram or the illustrations is shown on the right here, where we have three different components. We have the first one is a rigid reservoir where we can place the water, which is basically the medium to store the energy. And then we have the second one, which is the flexible reservoir that can be used to store the energy, just like what the movie has shown earlier. And of course, we have the third systems, which is the one that is responsible in storing the energy when there is an excess of energy by pumping water from the rigid reservoir to the flexible reservoir. And when we need the electricity back, what we can do is just to enable the turbine systems in the tree to be activated so that the water that has been placed in the flexible reservoir can flow through the turbines, and it's energizing the generator, and we can produce the electricity as what we demanded. And the water within the flexible reservoir will return to the rigid reservoir. So everything is actually in this case is a closed loop systems, and we are using fresh water mainly because we do not want to have issue with regard to the salt water interactions with all mechanisms within the systems. And it is a plug and play storage if we are talking about offshore wind farms. So we think and we believe that our solutions provide a utility scale offshore storage. So it is quick, affordable, and sustainable. And it is basically based on the hydro dam technology that has been proven by more than a century. Now, this is a comparison between the functioning of our ocean grazer, which is shown below, to the use of a hydro dam in order to store the energy. So the principle is basically the same. So if you take a look into the illustrations at the top, if you would like to store the energy using hydro dam, what we do typically, and this is also implemented a lot in the Nordic countries, is that when there is an excess of energy, we pump water from the lower reservoir, as shown in the middle, and the pump will bring the water through the penstock to the upper reservoir. And whenever we would like to produce the electricity back, what we need is only to open the valve in the penstock, which allows the water on the upper reservoir to flow back to the lower reservoir, thereby also rotating the turbines and generate electricity through the generator. So the principle is the same, but in our solutions, we are also using the hydrostatic pressure from the seawater. And in this case, then the deeper we are installing our device, the more potential energy that we can store in the same cubic meter of a flexible reservoir. That's the same in the hydro dam. The higher the higher hydro dam we install, the higher potential energy that we can store in the upper reservoir. So the basic principle is roughly the same. And if you try to compare the configurations of the ocean battery shown below with the dam, we can see the energy between 1, 2, and 3 over there. Now, why do we say that it is a utility scale? Because we can think of various different configurations depending on the need. We could also look at nearshore implementations shown on the 4, or we can also take a look into the use of our battery in offshore, where we couple it with the floating wind turbine as shown in the 1, or we could also combining it with the solar park offshore like shown in the 2, as well as we can combine it with the hydrogen productions offshore also shown in 2. And the third one is the one that we are also interested because it is combined with the wave energy converter that we are also developing in the lab at the university. This device is designed to be having a very high efficiency. A long lifetime is important because we are going to place it offshore. So then it needs to be able to withstand any conditions so that it can be operational for more than 20 years. And that's why we are looking into the hydro dam solutions, but underwater. And we are looking into modular solutions where we can cater for storage volume ranging from 2 megawatt hours up to the 8 megawatt hours. And it is also unlimited cycle in the sense that we are able to store and then generate electricity, store, generate electricity back and forth infinitely, similar to the functioning of hydro dam. And we have, in this case, more advantages in comparisons to the use of electrochemical battery systems. We have a small proof of concept in our lab, which is shown in these movies. It's very simple proof of concept that has been done many years back, where we are actually pumping water from the rigid reservoir to the flexible reservoir. And this is shown here that there is an electricity, or the pump is activated where water is now flowing to the flexible reservoir. And if we would like to start producing the energy, then we can open the valve through the turbine where we generate electricity. So in this case, due to the hydrostatic pressure, all the water inside the bladder or inside the flexible reservoir will flow back to the rigid reservoir. So this is a very simple proof of concept, and we move it further to other demonstrator, but I will try to show it later. We try to also take into account that we need to develop solutions that reduces actually levelized cost of electricity when we deploy renewable energy systems in offshore. And how we can reduce the levelized cost of electricity is by enabling the combinations with storage. And we have calculated that it can reduce the LCOE further down by 11%. Mainly these advantages is obtained by enabling optimal use of our renewable energy productions capacity. So we put some business case to this one, and in fact, indeed, the use of a storage device will enable us to have a return of investment in around 7 to 10 years, depending on the way we compute it. And this is actually the basis for our startup company. The market opportunities is tremendous at the moment, and I can also foresee that in Indonesia, since it is an archipelago countries, there are a lot of opportunity also to provide a stable electricity productions in islands, and the ability to store and use the energy in an infinite cycle allows us actually to really have a constant energy productions. So we try to bring it from the lab to larger prototype where we have conducted a really live demonstrator that we have realized in recent years. So that is the task that we have done in a real sea situations, where we have learned quite a lot on issues related to the real deployment in the sea environment. Of course, everyone knows that whenever you move from the controlled lab environment to the sea, you will always encounter problems. And in our case, we did not actually encounter a lot of problems. And the surprising things that we have learned from this real harbor test is that actually the surface of our battery systems becomes a really safe haven for oceans organisms. So we've seen that there are a lot of biological organisms that thrives on our platforms, and this is also one of the good sign that we are also eco-friendly solutions for the sea. And this makes us realize that actually by deploying our solutions, we can actually enabling the biological ecosystems underwater can be supported through our device, since it allows them to grow and also to live on the surface without actually jeopardizing the functioning of our systems. And that is important when we are looking at the North Sea, because in North Sea, the biological activities actually underwater has been really reduced in recent years due to the exploitations of the oceans. And largely in many places in North Sea, there are not many biological activities underwater. And with this deployment of this one, then it provides an eco-friendly solutions to allow them to grow back again underwater. This is the location. So the location is close to University of Groningen in the north. And we are also doing some kind of a survey on the locations to place the demonstrator. And this is where we are building our first demonstrator in the lab, where we assembled all the components. And we have recently undergo another design cycle to enable us to deploy large-scale solutions. And it is based on the use of a buried rigid reservoir, where we first dredge the ocean floor. We can place our structure over there, and that means it will be completely anchored in the seabed. And then the flexible reservoir again is placed on the bottom of the sea. Recent achievement that we have got, we've won, actually we are incorporated as a startup company in 2018. There are many awards between 18 until this year, but one of the highlights is actually that we won the Consumer Electronics Show 2020 in Las Vegas this year, early this year in January, and we are very proud of it because we won the Best Innovations Award in this conference. And recently as well, our startup company, together with other companies in the consortium where RWE is part of. So RWE is one of the largest utility company in Germany. We won a tender for a very large offshore wind park in the offshore of West Holland. So together with them, we are actually realizing our dream of having an integrated solutions for renewable energy productions offshore. So with that, I would like to conclude my plenary, and thank you for your attentions. I return back to the moderator. Thank you.
Thank you very much, Professor Bayu Jayawardana. Please give great applause for Professor Jayawardana. Truly innovative idea, and I think it's of great potential to be implemented in Indonesia. Professor Bayu Jayawardana, would you please wait for the next session, because we would delay the question and answer session after all the speakers deliver their respective lectures. And before we listen to Mr. Din Sharafi's lecture, I would like to invite all the audience to short coffee break. So please kindly enjoy the coffee here. And for the participants online, please have a short break in your respective places. And after the coffee break, it's about 5 minutes coffee break, we will have another speaker, Mr. Din Sharafi, and we will invite him to deliver his lecture. And then after that, we will have the third speaker, Professor Bambang Sujanarko. We invite him to deliver the speech. And then after that, we will have about 30 minutes question and answer session. So please kindly take note. And then in the question and answer session, please kindly ask your questions. Thank you very much.
Thank you.
Hello, Mr. Abdul Rahman. Can you hear me?
Yes, Mr. Sharafi. Yes, I can hear your voice clearly.
Okay, great. Thank you.
Thank you. Ladies and gentlemen, let's start the second part of this plenary session. We are going to learn from the second expert, Mr. Din Sharafi. I would like to introduce Mr. Din Sharafi. Mr. Din Sharafi is heading up the system design and transformation group of the Australian energy market operator. Mr. Sharafi holds a degree in applied physics, a degree in electrical engineering, and a degree in business management. He has around 30 years of experience in power system engineering, which includes power system protection, high voltage systems, asset management, and power system and electricity market operation. Mr. Sharafi is a member of Australian Institute of Management, SIGRE Engineers Australia, and a senior member of IEEE. Mr. Sharafi has been actively involved with IEEE Power and Energy Society initiatives and SIGRE working groups over the last decade. And he's currently a member of the governing board of the IEEE Power and Energy Society. Mr. Sharafi has published many papers on power system protection, condition monitoring, asset management, and power system operations. He also lectured for a decade as sessional academic on power system earthing at Curtin University in Western Australia. Ladies and gentlemen, let's welcome Mr. Din Sharafi.
Hello, and thank you very much, Mr. Abdurrahman. I hope you can hear me.
Yes, I can hear you very clearly.
Thank you, and thanks for the introduction. Let me share my screen. Hopefully you can also see my screen here.
Yes, we can see it.
Maybe, let me see. Okay, you can see it in a presentation mode, I hope.
Yes, it's
okay, great.
Very clear from my part.
Okay, thank you so much, and thank you for the invitation. I thought because the topic of this conference is about environment and how to go to net zero, I show you this graph in the beginning of my presentation. This is the emissions from 1940 up to now, and as you can see, the emissions have grown every year. There is a small change, and I think you can see it on top of this graph, and this is because of COVID in 2020, but this was just a blip in the trend of increased emission, and these emissions are going to increase even further if we don't address them. And I'm sure that you heard that last Tuesday, the population of Earth reached 8 billion people, and it's going to increase, and it is going to increase the emissions unless we do something about it. So this topic for this conference is very related and very timely, and we need to focus on what we can do to at least reduce emissions in our industry. So in the electricity production, which we have a great role to play here. The point is that electricity is local. It depends on the local policy, but emissions are global. So we need cooperation of everybody in this industry and global cooperation to reduce emissions and go back to what the Earth looked like, you know, before the Industrial Revolution, hopefully. So our progress should not mean that we increase emissions. And I think for Indonesia, it is a really good message because Indonesia have more than 1,400 islands, right? So we know, I think the exact number is 14,752 islands in Indonesia. Sorry, I said 1,400, but I meant 14,000 actually. And renewable energy is the best solution for Indonesia, because on these islands, you can have solar and you can have other renewable means of production of electricity like wind, and then you won't need diesel. You won't need to transport diesel to all of these islands and create an environmental issue. So the picture that I'm showing is one of those islands, and there are so many of them that this solution can be very effective. And let me explain a little bit what I want to say and what my company actually does in Australia. I work for AEMO, and AEMO stands for Australian Energy Market Operator, and we effectively operate the electricity grids in Australia, and also we operate the gas market in one part of Australia. But the focus of this presentation will be on electricity. And as you can see, that there are two sides of the country that we operate the electricity grid for. And I'm going to talk to you about the electricity grid in Western Australia. Why? Because Western Australia is the only gigawatt scale grid that is also an island. So it will be very important that in Indonesia, we are operating a lot of small islands as very like microgrids. But I'm going to talk about not a microgrid, but nevertheless a grid that is also operated like an island, and it's not connected to any other grids. So there is no interconnection in the grid that we operate in Western Australia. Okay, let me show you a few things. This is the mix of generation that we have in Western Australia. And as you can see, there is still some coal. So about 36% of coal still exists in Western Australia, and there is some gas. And the combination of coal and gas presents the fossil fuel that we still are using in our energy system. But you can see there is about 30% of wind, and that there is about 14% of distributed energy resources. So what are these? If, excuse me, if I showed you the same graph for 10 years ago, you would see a lot of black areas on this pie chart. And this is how we have reduced our reliance on coal, and we are continuing to reduce our reliance on coal in the next decade. So by 2030, there will be no coal in this part of the grid in Australia. But how? You can see a great share of other mix of generation like wind, solar, and distributed solar. And you can see that this share has increased year on year, and it is growing really very fast. What is this doing to the power system? And I think what will be important for Indonesia to get out of this presentation is that because of the distributed energy resources, so that is solar rooftop on people's homes, the load profile during the day becomes very low. And this is, you can see the number here, 761 megawatt is the load of one whole state. And you can see that, in some hours during the day, it will be very hard to manage the grid, because this amount of generation that comes into the grid is uncontrollable. So where are they coming from? They are coming from people's rooftop. And as you can see in this specific day, about 67% of underlying demand was supplied by rooftop PVs. 67% is a very, very high number. And you can think about a source of energy that comes into a grid without being controlled from a central plant, and also having a specific characteristics that I'm going to talk about how we are faced with a lot of challenges as a result of this. In Australia, 1 in every 3 homes have rooftop solar. 1 in every 3 homes. And well, I have a solar on my roof in my house, and most people in my suburb have the same. And you know, it helps us to have electricity, produce electricity and use it. But for the grid perspective, for the system operator, it creates a lot of challenges. So what are those challenges? What are the system impacts of these issues? We have very large load swings with days that are cloudy, and the clouds move from one part to the other part of the city. And those load swings sometimes are really very hard to manage. How we manage them? We enable a lot of ancillary services, so we can quickly respond to those cloud movements. As I mentioned in my previous slide, the lowering demand will create minimum demand issue. So I'm sure you know that for operating a grid, there needs to be a minimum stable operational demand, so we can rely on that demand to enable some generators that are really required for the system to keep operating. So as the demand goes down, those challenges will become more and more pronounced for us. We see fewer synchronous dispatchable generators to sustain power system security and reliability. So during early hours, as we face the minimum demand, we will have to turn off some of these generators that we need for the evening. And if we can't really get them back in the evening because of their inflexibility, there will be issue with supplying the load during the evening. We will see lowering system inertia. As you know, the synchronous generation will not only provide energy, but they provide other attributes that are really important for the power system. And inertia is one of them. The lowering level of inertia means the system can become uncontrollable if there is a contingency that needs to be managed. So inertia is an issue for the system, and I'm sure there will be an issue for the smaller system that you will be operating. But there is always a way of managing those challenges. So renewable generation is changing the frequency management requirements. As I mentioned, inertia or rate of change of frequency is one of the issues that systems with low synchronous generation always have to deal with. In our previous lecture, Mr. Bayu also talked about negative prices. We see that these system challenges create a lot of impacts for the market, meaning that when we go through those minimum load situations, that the market becomes negative. So the generators actually pay to provide energy. So this concept is really strange, but the fact that some of these generators cannot turn off and need to be operating during the day, when the market price goes to negative, they have to keep operating. So they have to burn coal, for example, they have to burn fuels, but still they have to pay to keep operating. And this is not a bad thing, but when you get those situations that the price goes to the floor price, it creates a lot of issues. So non-synchronous generation will soon exceed synchronous generation. The share of inverter-based generation is going to increase so much that they will be the biggest share of the generation mix. Why is it an issue? Because the power system has to have certainty for planning. Because if we don't have certainty, we can't plan for the power system. We need to have dispatchable generation so we can plan for it and make sure that we always meet the demand. And the share of non-synchronous generation, as it increases, the planning and the certainty will disappear. So there is an issue with that. And we have a stronger than expected growth in solar generation. For example, in the year 2020, when we had COVID and we had lockdowns and people could not go and spend their money on travel and go overseas, there was a lot of extra money for people, and they put solar on their roofs more than expected. So this growth is also going to be more and more. But these are the system impacts of renewables. I'm not saying that these are all challenges. It is really good for the environment. And we have learned how to deal with these challenges. For example, in South Australia, where the share of generation is inverter-based generation is very high, and we are facing system inertia and system strength issue. Now we have synchronous condensers. And in Western Australia, we are also thinking about synchronous condensers and how they can replace the retiring synchronous generation, especially coal that is going to retire in 2030. We have also created situational awareness tools for our controllers to be able to see the situation and ensure that we always operate the grid in a secure sort of way. So it's secure and reliable, because the power system does not give you an indication when you are running it in an insecure zone, unless something happens, and then you will see that you have been insecure. So are all these challenges are really preventing us from going to net zero? No. Operating at 100% renewable system is not mission impossible. So we have already designed a system with 100% renewable islands with grid forming inverters. I think this is very important for Indonesia when operating the small islands, to be able to specify the technology that is required to operate securely, and grid forming inverters is one of those technologies. So what is needed for Indonesia? What is needed for those small islands that you operate? Of course, you have plans, and I've read your plans to go to net zero. And I think it is important that from this presentation, you see all the challenges that you will be facing if the energy transition goes very fast and the right technologies are not in place. So we say we need firm renewables. So renewables previously had a very small share in the power system. They were like 3%, 10%, 15%, and those small percentages are manageable. But when the share of the generation, which is produced by inverter-based technology, we need certainty, as I mentioned. So we need firm renewables, meaning that renewables must be firmed with storage and other technologies that exist. Like the previous presenter, Mr. Bayo, talked about ocean battery. So that is one technology that I'm sure it is very relevant for Netherlands. Is it relevant for Indonesia? Maybe it is, because you are very close to the ocean, and you have the sort of topography that really can be used for that sort of technology. So firm renewables is something that we will need for the future of the power system. We need grid forming inverters, because for small systems or for larger system with a lot of inverter-based technology, if the inverter technology is grid following, it needs a voltage input to operate securely, but voltage input with large share of inverter-based technology is not going to be a very solid input. So we need inverters who have their own voltage source, and we call them grid-forming inverters. As I mentioned, because we started this transition to net zero in the last decade, it has taken effectively 12 years until now, maybe a little bit more. So those this distributed PVs were not controllable. There was no means of controlling them. But I think for you, because you are starting to do this now in those small islands, you must have visible and controllable distributed energy resources. This is really very important. If they are not controllable, you may not be able to control some of these islands securely. The right control technology should be in place for you, such that those power system, those microgrids can be controlled effectively. And you need a sustainable mix of generation types. It is really important that we don't rely only on one generation type, because, for example, if we only rely on solar, you need a huge storage type for when the sun is not shining, for example, at nights, or when periods of rain continues for a few days. So the right source of and the right mix of generation is becoming very, very essential. So I would say, you have to establish what is the source of those generation types, the source of fuel like wind, solar, and storage, to sustain you for those small microgrids that you're going to operate. And we need the skilled resources. I think the industry in the last decade has really not taken up what we should do in terms of upskilling workforce. What we are facing here globally, and specifically in Australia, is a shortage of a skilled workforce. And this is something that you can't really create in a very short period of time. So utilities should really focus on how we can create a skilled workforce for the challenge that is lying ahead. And we really need a multidisciplinary approach. So the days that the power system only required electrical engineers or power engineers have gone. We need a very multidisciplinary approach, because now in energy, we have policy, we have data science, we have information technology, and there are so many things. We have economy that also need to be addressed. So the economists are also needed, and we need regulatory people. And we need all of these to work closely with politicians, because as I said in the beginning of my presentation, energy is really very political, and every government really engages in how the energy system should work, and policy can be really a very effective way of addressing some of these challenges. And university have a critical role. And I think you, in your university, you are addressing those, because the topic of this conference is very wide. It's not only about the power system, but it is also about information technology, about data science, and about all of these multidisciplinary aspects that we need to operate the modern power systems. So thank you very much. This was my presentation, and I hope that there has been something for you out of what I have shared with you.
Thank you very much, Mr. Din Sharafi. Please applause for Mr. Din Sharafi. It's very interesting that Mr. Din Sharafi take analogy between Indonesia and Australia, that both have islands, and Australia is a large island. So the electrical system should have similarities. That's very, very nice. And I believe that we can have rich discussion on every aspect of what you have mentioned. But we will delay the question answer session. Please take notes and then prepare your questions. Now we are going to listen to the lectures from Professor Bambang Sujanarko, our third speaker. And Professor Bambang Sujanarko is currently a professor of electrical engineering at the Faculty of Engineering, Universitas Jember. He is the head of Renewable Energy Laboratory at Center for Development of Advanced Science and Technology, Universitas Jember. He is also a senior member of IEEE and a member of Expert Council at Institute of Engineers of Indonesia, Jember chapter. He's also senior professional engineer certified by Institute of Engineers of Indonesia, or PEE. Professor Bambang Sujanarko earned the bachelor degree in electrical engineering from Gajah Mada University, Indonesia in 1989. And then he earned master degree in management from Universitas Jember, Indonesia in 2005. And he completed his doctoral study, and he received the degree in electrical engineering from Institut Teknologi 10 November, Surabaya, Indonesia in 2012. He has published numerous papers, including papers in power electronics, wind energy, solar energy, and electric vehicles. Ladies and gentlemen, let's welcome Professor Bambang Sujanarko.
Okay, thank you, Mr. Abdurrahman, and good morning, everybody. Okay. Good morning to Mr. Din Sharafi and also Mr. Bayu Jayawardana. Okay, in this my present, I will present a topic that related that presented by Prof. Bayu Jayawardana and also by Din Sharafi. It's about how Indonesia contributed to achieving the Paris Agreement target, especially those related to the concept, regulation, and implementation of distributed photovoltaic. This review is urgently needed, considering distributed photovoltaic is a best choice to overcome the gap between the target of Paris Agreement Indonesia, Paris Agreement in Indonesia, and achieving the use of renewable energy. The first background of my topic is the excite of climate change, like Dean Sarafin talk earlier, and also moderator talk in the previous session. And also about fossil energy use problem. We know that there is an increase of temperature because energy burn every time. It's increased carbon emission that cause greenhouse effect, and then the Earth is 1.1 Celsius degree warmer than it was in the last 18th century. To avoid the word climate impact, the Earth must be lower than 1.5 Celsius degree by reduction of fossil energy use. If not controlled, the burning of fossil energy will become increased. The temperature become 2.x Celsius degree by the end of the century. Next, we know that this graph of the use of energy in the world began around the 1950, dominated by fossil energy. You can show in the screen. Coal, oil, and natural gas is dominated. Since the year of the use of fossil energy has increased drastically, and reached more than 80% of the world total energy use. So there is 80% of the world total energy use. And 2021, the total energy use in the world is 179.431 terawatt hour. In this year, renewable energy use only 28.1%. In this screen, you can this data. In the from next graph, okay, next slide. We can show that how temperature in the world increase from 18th century until now. In the now, the average temperature is 13.3 Celsius degree. Temperature rise about 1.4 Celsius degree, like shown in the graph. From the thin to 14. Yeah. In the next graph, its slide also have been shown by Din Sarafi about the carbon emission. We can show that carbon emission increase average 2.7 gigaton per year. But in this graph, we can show in 2019, it's decreased about 5.4% because it's in pandemic condition. We know that in pandemic condition, more person not mobile. Yeah. Like also in 19H, yeah, there are global financial crisis. There are decrease of global fossil carbon emission. Next. Nah, because the problem of the environment, many countries then committing to get net zero emission by 2050 and by 2030 keep warming below 1.5 degree Celsius. Nah, one solution is switching energy system from fossil fuel to renewable energy, like discussed by you and Din Sarafi. There are 196 countries in Paris on December 2019, committing to control global warming effect using reducing fossil energy burning to achieve net zero carbon and switch it to renewable energy. So in this agreement, they are committed that by 2020, countries submit their plan for the climate action known as nationally determined contribution, NDCs. Okay, next slide. Now, in this picture, we illustrate that in the upper line, it's shown that if we not control about energy use, we can temperature, yeah, we can get a temperature in the world is increase about 1 to 4 degrees Celsius. Yeah, like in the bar graph in the right side. Yeah. If in the second line, you can show that it is a graph if we low policy of control of energy use. And then we can hope using control energy use by switching fossil energy to renewable energy. Yeah. We can get increase energy about only 1.5 degrees Celsius. This line is commit by 196 countries. Okay, next slide. Yeah, we can know that in the human life depend on electric energy. In all world, we depend electric energy. So we can show in the graph that solar PV, it's the best choice for next year, yeah, next time about fulfill of energy use. Why the solar power is the best choice? We can show in the next slide. Solar energy is the most abundant and the cleanest renewable energy source available. Every area on the world also get solar radiation. So it's the solar radiation is abundant and cleans renewable energy. Now, to overcome the climate change and also another effect of use of fossil energy, we must switch energy use to renewable energy. Yeah. It means that more use of solar PV and switch order from energy necessity to electricity energy. But it's not and other energy. Yeah? The energy must be calculated too. Solar PV as a solution because solar PV has low levels cost of energy. Provide you say in the next session that wind also low levels cost of energy. Okay, in the next slide. It is a potential of energy in the world. We can see in the right side, it's solar is have highest potential than others. There are 23 gigawatt pentawatt per year. Nah, in recent, we use coal, oil, and natural gas, but it's limited reserve energy. But solar energy is not unlimited. It's unlimited energy. So the best choice is we use solar energy to fulfill energy use in the world. Okay, in the next slide. It's the second reason about why we choose solar power as a solution. Because solar solution has carbon emission, low carbon emission. Nuclear power has lowest, but it's high low level is cost of energy higher than solar energy. Next slide. Other reason about solar power choice is solar power have chief of investment. It's low of levels cost of energy. Also a low of investment. Okay, next slide. Nah, it's a prediction about how the world fulfill of energy by source until 2021 in the facts. It's more than 60% energy worth supply by fossil energy. Okay, next slide. It's installation about solar photovoltaic in the world in gigawatt until January 2022. Okay, next slide. How solar panel policy in Indonesia? We know that Indonesian is a very rise in solar energy, like Din Sarafi say, because in Indonesian is archipelago of a country, and there are many and renewable energy also we can find in Indonesian. So Indonesia also have been mixed energy in the 2030 and 2040 target. Yeah, we have target about the mixed energy. And then implementation of solar PV, especially distributed photovoltaic, is very slow in Indonesian. Yeah. Very slow in Indonesian. Australia is high the best, yeah, the best. Another country is Chile. There are, and Chile is highest country implement of solar PV. Indonesia need regulation synchronization to make distributed photovoltaics investment attractive. So in the next slide, we can get a description about this statement. Indonesian rise about solar power. You can see in this graph that in the island near Australia, there are highest solar PV. Ya. Nah, solar energy in Indonesian is 89%, 89% of total renewable energy. Yeah. You can think about this energy. Yeah. It's very big energy than others. Yeah. In the next slide. Nah, it is a share of primary energy from solar in the last year. You can see Chile 6%, kemudian and then Australia 5.14%, yeah. And Indonesia only 0.02%. Yeah. It's very low, very low than other country. In the next slide, also we can show that the graph of Indonesian implementation about PV compare that other countries. Indonesian has potential of energy on PV about 2,000 300 times than last year electricity consumption. Very high energy potential. Okay, next slide. This is a policy of government about target of renewable use in Indonesia. Yeah. You can see in the next target is 2025. Yeah. 2025. Yeah. And the paragraph, it's a PV install until last year. Okay, next slide. We talk about solar power technology in Indonesia. In Indonesia, research on solar PV and DPV has been sufficient. More paper, more experiment has been done in Indonesia. And the second, solar cells and electronic component still import. It's disadvantage of solar technology in Indonesia. Yeah. And the third, there have been a number of solar PV installation ke Malaysia. Technology solar power in Indonesia usually install using off-grid and also on-grid or grid tie. Okay, we can next slide. We can show in the next slide. It is a kind of solar panel, ya, solar power. Ya. There are monocrystalline, polycrystalline, and thin film. Ya. And the high efficiency of among three kind of solar power is monocrystalline, but it's highest price, highest price among the other. We can show the technology of photovoltaics in the next slide, that photovoltaic can be divided into 3 generation production. In the left is the first generation, in the middle is second generation, and in the right is third generation. Okay. Next slide. We can show that PV system in Indonesia, there are many kind of PV system. The first is grid connected, like the early talk. Kemudian standalone PV system. We hope that PV install Indonesian in grid connected PV system. Directly coupled bimodal PV system, it's not problem. How the power grid system install? You can see in the next slide. There are many PV system. Usually in Indonesian, in Australia, it's rooftop PV. Dean Sarafi saying that's among 3 house, 1 house is install PV. We hope in Indonesian also like in Australia, there are many PV, rooftop PV install in Indonesia. This power grid need synchronize about grid and the power produced by solar power. This usually by using inverter, But to adjustable power voltage, power voltage, we use converter, DC to DC converter. Many kind. We have research about DC to DC converter and also about inverter. Okay, in the next slide. PV power plant installation, we can divide into 2, in the 2 category. The first is fixed mounting. There are land-based or onshore, and then offshore, like Mr. Bayu say, install about wind in offshore. Then in rooftop, in floating, usually in the sea or in the water of lake, on the lake. Also, fixed mounting usually implement in public street lighting. In Indonesia, many public street lighting use solar PV. The second category is tracking PV. Yeah, usually single and dual axis tracking. We have many research about single and dual axis tracking about a PV. Okay, we can show the next slide about 20 largest solar power plant in the world. The first solar panel installation is in India. India is have a biggest solar panel solar plant in the world. China have more power plant, and China is the hiker of power plant installation in the world. Okay, next slide. It's in the slide we can see 10 largest floating solar power plant in the world. In China is the first. Yeah, the name is Three Georges. Indonesian, plant have the bigger of floating solar power plant on Batam Beach. On Batam Beach will be built about 1 gigawatt peak solar PV. Australia also will build on the Northern Territory, like in the Batam Beach, because the electricity produced in this in Batam and Northern Australia will be exported to Singapore. Singapore committed to Paris Agreement. The country will be to meet Paris Agreement early than other countries. Okay, in the next slide, we talk about 10 largest rooftop solar power plant in Indonesia. The first solar rooftop in Indonesia is installed in the next slide. Ini rooftop Indonesian in next slide in Indonesian. Install in PLTS Waduk Cirata. Nah, anybody arrived in Cirata? Okay, this is 10 of largest solar power plant in Indonesia. Okay. Under construction, PLTS Kepri, it's export to Singapore. Like, okay, next slide. About regulation solar PV in Indonesia, start in 2015, yeah, 13. Yeah. And the last regulation is produced in 2021, but this regulation is postponed. Why postpone this regulation? In the next slide, we can show that the reason of the postpone of regulation. Next slide. Because solar PV installed in rooftop potential decrease in PLN revenue. We can show that Indonesian in oversupply of electric energy. So government saying that if we continue the regulation, its potential to decrease PLN revenue. In the second, is the lack of incentive and mainly related to selling price of electricity to PLN. There is no attractive of price. The third need to synchronize the change in net metering provision to electricity export from 85% to 100%. There is not synchronous about policy in budget minister and energy minister. And the fourth is unfinished application system. Jadi, many application not finished. Okay, in the last slide, okay, there are many recommendations of distributed photovoltaic in Indonesia. The first is shifting the use of fossil energy to electrical energy to overcome oversupply of electricity. We must shifting use energy to electric energy. And the second is innovation of financing and incentive as compensation of subsidy. Indonesian have about 20% of budget government is for subsidies. So its subsidy must change to innovation financing in the renewable energy. And the third is selling and buying price adjustment. Need selling and buying price adjustment like Prof. Bayu say. And then the end is establish solar PV factory to decrease dependence of import component of solar PV. Okay, it's the end of my presentation. Thank you very much.
Thank you very much, Professor Bambang Sianarko. Please give applause for Professor Bambang Sianarko. Ladies and gentlemen, and now it's the time for question and answer. So I would offer the first opportunity to audience in auditorium of Faculty of Engineering here. If you have any questions, please kindly raise your hand and then introduce yourself and your institution. And please explain to which speaker your question is addressed. And then for the audience in Zoom, if you would like to deliver your question orally, please kindly click raise hand, and then I will give you a chance to speak. Or alternatively, you can write down your questions in the chat room by introducing briefly your name and your institution, and then please kindly write down your question clearly. Any question from the audience in the auditorium, please? Okay, while waiting for the question, actually, I have a list of questions for each of the speaker. First of all, I would like to ask to all the speakers, Professor Bayu Jayawardana, Mr. Rin Sharafi, and Professor Bambang Sianarko, about the market structure, the different market structure that Indonesia has. Because from the presentation of Professor Bayu Jayawardana, the ocean grazer with pump storage in the bottom of the ocean, I think it's profitable only when the price of generating electricity and the price when the pump raise the water back is different. And also in the presentation of Mr. Din Sharafi, Mr. Din Sharafi talked about the market, about the price, and Indonesia, as you may have known that our system is vertically integrated and our market is not liberated. So what do you see? What's your thoughts about this difference in market structure? How Indonesia can make the best use of, for example, the technology that Prof. Bayu Jayawardana offered, while we have strict policy on electricity price. Maybe Professor Bayu Jayawardana first.
Okay, so thank you, Pak Abdul Rahman, for the questions. Indeed, the Netherlands market is a liberalized market in the sense that there are many market players in the electricity market, and both the consumers and producers can benefit from having this liberal market. And I think in Indonesia, although you might think that Indonesia is a vertical structure with PLN as the main subsidiary for the electricity, but when we are talking about renewable energy, then in my point of view, the interactions with other energy companies in Indonesia will be prominent in the coming years, like Pertamina or any other energy companies. These are basically, we are talking about energy. We are not talking about electricity, we are talking about energy. So if we are talking about renewable energy, then there is a possibility that actually the market in Indonesia can be liberalized in some sense. Maybe that's just my point of view.
Professor Jayawardana, Mr. Din Sharafi, what do you say about this?
Yeah, I have a slightly different view, and my point of view comes from operating a market for more than a decade in Australia, and I think if Indonesia has long power purchase agreements and can avoid a liberalized market, then probably that is the best option for Indonesia, because once the genie is out of the bottle, you can't put it back. So, and if you go with a very complex market structure, that there is potential for market failures and a lot of unnecessary work. And I would say have a look at the America, where they went into creating a market, and maybe those who didn't go in a market like cooperatives have a better really experience with lower prices and not having to deal with a lot of regulatory approach and a lot of law firms that operate in the liberalized electricity markets. It's a huge industry by itself, and if utilities think that they are missing out on something, but in not having a market, I would say if market doesn't make sense for you, try to avoid it as much as possible. If you have long-term PPAs in place, maybe there is no point in having a liberalized market.
Thank you very much. So this is a very interesting perspective from Professor Jayawardana and Mr. Din Sharafi. So I think our lawmakers should consider this. Okay, Professor Bambang Chanarko, what do you say about this market structure?
Okay, I agree about statement of Mr. Bayu and Mr. Dean. About this price and policy of energy in Indonesian must be talked about inter minister. Yeah. There are minister of financial, minister of energy, mineral, renewable, also in government BUMN ya, government the sector of public of apa ya in privacy of industry. So I think that synchronization about policy in Indonesian. But in short time, I think in the renewable energy application is PLN like Pertamina must switch to renewable energy. It's to keep the human resource in the PLN, Pertamina, and others industry.
Okay.
I think it's good.
Thank you very much, Professor Bambang Sianarko. Next, we have a question from Asaida from Sriwijaya University. This question is addressed to Professor Bayu Jayawardana. What is the minimum size of the propeller to produce electricity? Yes, Professor, please.
Right. So thank you, Bu Saida, for the questions. I think this is a bit a technical question that I need to ask to my team. But since we are talking about 2 megawatt hours this is already very early morning in Netherlands.
Oh, sorry.
Ocean battery systems. It's the size of propellers is in the meter size, but a precise number I need to ask to my team. I think I cannot answer immediately that questions.
Okay, thank you for Professor Bayu Jayawardana. But I have one more question for you. You said that in your proposed design, you use fresh water to avoid problems with salt water. And this directly poses a question because we need fresh water. So there will be fierce competition, fresh water for energy or fresh water for consumption. So what do you say about this?
I think in this case, indeed, the amount of fresh water that we require may compete with other usage as well. And in that case, it is unavoidable that we need to really divide the sharing of resources. An alternative to using the fresh water is, of course, we use the conditions liquid, but then we need to again put some energy to create some conditions liquid for the element in the ocean battery systems.
Oh, I see.
But that is something that is unavoidable.
Oh yeah. Okay. Thank you very much, Professor Jayawardana.
And one thing that I would like to add here, maybe, the main reason why we use the fresh water is first of all, is that we would like to avoid corrosions and other unwanted interactions. But also, if we are only using water, and when there is something happening with our device, let's say it's kind of like there's a puncture in the flexible reservoir, then it is not creating an environmental disaster. In comparisons, if we are deploying an electrochemical battery systems offshore, when something happens to these systems, then it's going to create an ecological disaster, which is not what.
Materials.
Yeah.
Okay, thank you very much, Professor. And then any other question from the audience here in auditorium? Okay, Mr. Din Sharafi, I have a question for you. You explained several things about how to anticipate the great supply of PV, for example, or in general, how to keep the stability of the system. But I didn't find any mention about demand side management. for example, demand response? Is it a part of strategy that has been implemented in Australia?
Yes, thank you very much, Dr. Abdul Rahman. Yes, and I didn't speak about demand side management, but yes, this is one of the new initiatives that now we are pursuing in both sides of Australia. In Western Australia, there is a project, we call it Project Symphony. And the objective of this project is to see how we can aggregate the distributed energy resources and put them in a size that then we can bid them in the electricity market. And this is to provide energy or sometimes to reduce output. So the objective is to see how we can do a few things. One is to dispatch to zero from distributed energy resources. So we see a little bit of demand on the grid. The other one is to see how we can participate in the electricity market with distributed energy resources. And the other objective is to see how we can actually support the grid with essential system services like droop response from distributed energy resources, voltage response, and there are other sort of objectives as well that we are putting them in practice. So this is Project Symphony in Western Australia. And in eastern part of Australia, there is a project, we call it Project Edge, and also having the same sort of objectives, mainly to aggregate distributed energy resources and see how we can best orchestrate those energy resources to support the grid and also enable customers to still put rooftop PV on and benefit from reduced cost of energy that they can produce. So two projects, and maybe it will be a topic for future conferences.
Yeah, that's a really great idea for the future conference. Thank you very much, Mr. Sharafi. And Professor Bambang Sianarko, I would like to ask you about is there any significant relationship between controlling the large supply from PV in the day and the lack of supply in the night, and the recent development of electric vehicles in Indonesia? So in my understanding, probably we can just use the excessive power from PV to charge the electric vehicles. What do you think about this?
Okay, in my recommendation, there are a shifting of fossil energy use to electricity use. One of this example is shift to vehicle use petroleum to electric vehicle. Many ways to charge electric vehicle. They are from electric grid or in renewable energy. But we can talk about how to reserve electric energy in grid, because if we can reserve energy in grid, what use all of use is become overcome. So distributed photovoltaic is one choice to its.
So it's possible.
It's possible.
I see. Okay. Thank you very much, Professor Bambang Sianarko. Any question from the audience? Yes, please. Oh.
Okay, sir. My name is Rizky Aprianto. I'm from Jember University. And my question is for Professor Bayu. Sorry, sir. Maybe I still don't understand about the function of object that are places under the seawater. Is it for is it only for energy storage and distribution, or can can it be used to generate energy also by utilizing ocean wave, or just to save space because it is placed under the seawater?
Thank you very much, Mas Rizky, for the question. So Professor Bayu Jayawardana, Mas
Yes,
Rizky
so
asking about.
thank you, Mas Rizky, for the questions. I would like to clarify here that the use of ocean battery systems is similar to any battery system that you can deploy in land. So basically, you can store energy there, and the storing energy there is basically energy that comes from solar PV or from wind power, wind turbines, or can also be from a wave energy converter. You can store those energy into the ocean battery systems. And then when you would like to get the electricity energy back to the grid, you can reverse the process, and then you can generate the electricity from the ocean battery systems. So indeed, it is just for storing the energy coming from the renewable energy sources. And the functions of it is multi-purpose. It's basically to stabilize the electricity energy productions, but also to really utilize optimally the renewable energy sources. So I think that is probably the answer that I can provide at the moment.
Professor
I hope that clarifies
Jayawardana,
your questions.
excuse me. I would like to just to make it clear for all of the audience here. Do you use the only fresh water to to generate electricity, or you also use the motion of the wave in the ocean?
Okay, so that is an additional element. So we can try to decouple several different technology here.
Oh, I see.
Wave energy converter, and the wave energy converter is just to extract energy from the wave, and then you convert it into mechanical energy, or you can directly convert it into electricity, or you could also convert it into a potential energy in the ocean battery systems. But the wave energy converter is completely decoupled to the story about the ocean battery systems.
Okay, thank you very much. Is it already clear, Mas Rizal? Thank you very much for your question. And yeah, Mas Rizky, sorry, Mas Rizky. And because of limited time, I have one last opportunity for the audience. If you want to ask question, for the online participants, please kindly raise your hand. Or if for this last question, you are more comfortable to say in Bahasa Indonesia, just ask your question in Bahasa Indonesia, and I will do my best to translate it for you. Anyone? Anyone, please? Yes, please. Yes, please.
Okay, may I speak in
Yes.
Bahasa?
Yes, please.
Okay. Before, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Di sini saya punya pertanyaan untuk Profesor Bayu. Kan tadi dijelaskan itu sebuah inovasi bagaimana membangkitkan energi listrik menggunakan gelombang air laut gitu ya, Pak.
Ya.
Di sini pertanyaannya saya, apa yang terjadi jika ada suatu kondisi di mana air lautnya itu ada badai? Apakah itu akan
Badai.
ya
Apakah itu akan merusak infrastruktur atau akan membuat energi listriknya itu semakin banyak gitu, Pak?
Mas siapa?
Fajar, Pak.
Okay, thank you very much. Mas Fajar is asking a question about how if there is a storm in the middle of the sea, will it destroy the system that Professor Jayawardana proposed?
Terima kasih Mas Fajar atas pertanyaannya. Thank you Mas Fajar for the questions. And indeed, that is a really relevant questions whenever we design any complex engineering systems. And in particular for our wave energy converter, because maybe not all of you knows about the potential from coming from the wave. So the wave, if you are looking into the offshore of Ireland, or maybe even in the south of Australia, the range of the wave can range from 2 meter up to 20 meters. So it is called like freak wave. You can imagine 20-meter wave that's very, very high. And the target operations for our wave energy converter is only ranging from 2 to 8 or 12 meter. So we are not aiming for a 20 meter. And whenever there is a storm happening, there is a kind of like fault tolerant mechanisms embedded into the systems, whereby we actually disabled our wave energy converter. So what's happening is that when such freak wave comes into the platform, we lower all the floating elements, and everything will be actually becoming submerged into underwater, and then it will remain unoperational for some time until the storm has passed. And when it is already passed, then it is back into the operational.
Thank you very much, Professor Jayawardana. Please give me a time to translate back. Mas Fajar, jadi menurut Profesor ini, alat yang beliau desain itu memang didesain untuk ketinggian gelombang antara 2 sampai 12 meter. Jadi kalau sampai ada gelombang besar, badai misalnya 20 meter, akan ada mekanisme yang mematikan ya bagian yang membangkitkan energi dari gelombang, dan kemudian bagian-bagian yang terapung itu semuanya ditenggelamkan dulu sampai badainya berlalu. Jadi menjaga keamanannya seperti itu. Jelas ya, Mas? Okay, thank you very much. It's very unfortunate that our time is up for this question and answer session. So thank you very much for Professor Bayu Jayawardana, Mr. Din Sharafi, and Professor Bambang Sujanarko. As probably a closing remark, so in this discussion, we have gained more knowledge about more interesting alternatives on renewable energy resources. For example, that has been introduced by Professor Jayawardana, and because Indonesia has large potential of ocean, so it's very good to consider and to learn and to experiment. And then we have also gained more knowledge about the operation of the power system, as Mr. Din Sharafi showed us for Australia, which is also a big island similar to islands in Indonesia. And also Professor Bambang Sujanarko informed us the great potential of PV, and also its possible usage along with the development of electric vehicles. And we get the point that we need storage technology with high quality for firm renewables. And then we need robust control for distributed energy. And also, I remember the point delivered by Mr. Sharafi that we need to have sustainable mix. And the last important point is that we have critical role. We as university, we academician, we have a critical role, because to provide a sustainable system, we need multidisciplinary approach. Again, thank you very much for Professor Jayawardana. Thank you for Mr. Dean Sharafi and Professor Bambang Sianarko and all the audience who have participated in this session. See you next time. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you very much. See you.
Thanks, moderator, for the time given. Dear distinguished delegates, for the empty cup and plate, you can put on the table in the bag that already provided. It was in your right bag. Next, we would like to invite the speaker to come forward to take a group photo. Bapak mungkin tamu undangan juga bisa. Oh iya. Pak. Lebih rapat. Sama aja. Tapi kurang, ya mohon maaf ya Bapak. Bapak mungkin bisa di atas. Mungkin bisa di atas. Mari Pak. Ayo. Semua yang berada di sini ini dilepas apa ditaruh sana kayak gini bisa semua ya. Ini di luar ya. Di luar ada bawah. Ayo semua foto sini. Biar saya Mas.
And don't forget to fill out the registration form with your full name for certificate needed. Coming up to the last session, we are going to have a parallel session. Please be noted that our session will start at 1 p.m. After break and lunch, you can proceed to your presentation room at ISTP building. Thank you.
Oh iya. Sebelum aku apa, ingatin dulu. Kami.